Welcome to Bite Me. Well, we're smashing bugs one bite at a time. Today we're going to be talking about Structs. We're on chapter 5 of this live. I'm happy that you're here with me, and let's jump into the video, okay? Okay, using structs to structure related data. A struct or structure is a custom data type that lets you package together and name multiple related values to make up a meaningful group. If you're familiar with an object-oriented language, a struct is like object data attributes. In this chapter, we'll compare and contrast tuples with structs to build on what you already know and demonstrate when structs are a better way to group data. We'll demonstrate how to define and instantiate structs. We'll discuss how to define associated functions, especially the kind of associated functions called methods, to specify behavior associated with the struct type. Structs and enums, discussed in Chapter 6, are the building blocks for creating new types of program domain to take full advantage of Rust compile time type checking. Okay, structs is a very important concept, and we're going to be using it a lot, especially when we're trying to build Solana smart contracts. They use all structs in Rust. So this is something that you really should get into. Okay, first, defining and instantiating, I think that's what it's called. Instantiating structs. Structs are similar to tuples discussed in the tuple type section, in that both hold multiple related values. Like tuples, the pieces of the struct can be different types. Unlike with tuples, in your struct, you'll name each piece of data so it's clear what the values mean. Adding these names means that the structs are more flexible than tuples. You don't have to rely on the order of the data to specify or access the values of an instance. To define a struct, we enter the keyword struct and the name of the entire struct. A struct's name should describe the significance of the pieces of data being grouped together. Then inside curly brackets, we also define the names and types of pieces of data, which are called fields. Look at listing 5-1. See, we got active, bool, we know is true or false, username, which is a string, email, which is a string, and then we have sign-in count, which is a U64 or unsigned 64-bit integer. To use a struct after we defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then add the curly brackets containing key value pairs, where the keys are the names of the fields and the values are the data we want to store in those fields. We don't have to specify the fields in the same order in which we declared them in the struct. In other words, the struct definition is like a general template for the type. And the instance fill in the template with particular data to create values of that type. Okay? For example, we can declare a particular user as shown in listing 5-2. Okay, so we have a main function here. We bound user1 to this new struct called user. We have active, which is true, username, which is a string, some username 123, email, which is another string, someone and example.com, and we have sign-in count is 1. To get a specific value from a struct, we don't use dot notation. For example, to access the user's email address, we use user1. Oh, I thought we don't use. We use dot notation. My bad. We use user1.email. So you can see here. Okay, let's finish this. If the instant is mutable, we can change a value by using the dot notation and assigning it to a particular field. Listing 5-3 shows how to change the value in the email field with a mutable user instance. Okay, so we have here what we had before in our main function, but over here we're going to use dot notation. So user1, which is right here, we have this variable user1, and then we're looking within that variable to destructure it using dot notation, or we're indexing it in a way. We're equating this to string colon from, and then we're changing it to another email and example.com. So simple stuff. Okay. Note that the entire instance must be mutable. Rust does not allow us to mark only certain fields as mutable. As with an expression, we can construct a new instance of the struct as the last expression of the function body to implicitly return the new instance. Now, listing 5-4 shows a builder user or build user function that returns a user instance with a given email and username. The active field gets the value true, and the sign-in count gets a value of 1. Okay, so we have a function called build user. We have 2 parameters, email and username, and returning a user. Over here, we have our struct, which is user, active true, user is username, email is email, and sign-in count is 1. So it makes sense that to name the function parameters with the same name as the struct fields, but having to repeat email and username fields and variables is a bit tedious. If the struct had more fields, repeating each name would get more annoying. So luckily there's a convenient shorthand. So here's the shorthand, okay? Because the parameter names and struct fields names are exactly the same in listing 5-4, we can just use field init shorthand syntax to rewrite builder underscore user so that it behaves exactly the same but doesn't have the repetition of username and email as shown in listing 5-5. So you can see here, like, we have this function build user, we have these parameters, but within here we have username and we don't have anything, we have no colon next to it, so it's the same one as the parameter, you see? And so it automatically knows that we're utilizing the same parameters. Here we are creating a new instance of the user struct, which has a field named email. We want to set the email field value to the value of the email parameter of the build user function. Because the email field and the email parameter have the same name, we only need to write it. We only need to write email rather than email colon email. So we only need to write it once. Creating instances with struct update syntax. Oh my goodness, I'm like stuttering so much today. I can't help it, I'm sorry. It's just how I talk. It's often useful to create a new instance of a struct that includes most of the values from another instance of the same type, but changes sometimes some of them. You can do this using struct update syntax. First, in listing 5-6, we show how to create a new user instance in user2 in the regular way, without the update syntax. We set a new value for email, but otherwise use the same values for user1 that we created in listing 5-2. Oh, there's a fly in here. We don't need that. Okay, so in our function main, we have let user2 as a variable bound to a struct, which is named user. Then we have active user1, and then we have dot notation of active. We have user1 dot notation username, and then we have another example, email sign-in count is user1 dot sign-in count. So using update syntax, we can achieve the same effect with less code. As shown in listing 5-7, the syntax ... specifies the remaining fields not explicitly set should have the same value as the field that is given in the instance, okay? So you can see this ... notation right here, which is showing us that user1, this new user2 is the same as user1. All the fields except maybe the email is different. The code in listing 5-7 also creates an instance in user 2 that has a different value for email but has the same values for the username, active, sign-in count fields for user 1. The .user1 must come last to specify the remaining fields should get their values from the corresponding fields in user 1. But we can choose to specify values for as many fields as we want in any order, regardless of the order of the fields in the structs definition. Fun. Note that the struct update syntax uses an equal sign like an assignment. This is because it moves the data just as we saw in variables and data interacting with move section. In this example, we can no longer use user1 after creating user2 because the string in the username field of user1 was moved to user2. If we had given user2 new string values for both email and username, and thus only using the active and sign-in count values for user1, then user1 would still be valid after creating user2. Both active and sign-in count are types that implement the copy trait, so that behavior we discussed on stack only and copy section would apply. We can also use the user1.email in this example because its value was not moved to user1. So like we were talking about within the stack only, and we're talking about the heap in the stack, there are certain traits that are able to be moved or copied onto another variable or another area, I guess moved into another area. We call it the move. And that is only if it's on the stack, okay? So things that we already know, the amount of bits that it holds and allocated in memory. Things like a string that are, I say big string with the big S, are not able to be moved like that, okay? Usually we'll have to clone them. In this section, it's telling us that we're not able to use the emails, which are strings, in user 2 because we already used them in user 1, because that would be a move, and that's not allowed. We're not allowed to do shallow copies, okay? Hopefully that makes sense. If you don't understand what I'm talking about, please go back into the previous episode. I think it would be chapter 4? Chapter 4. I think chapter 4 is where it goes into borrowing, ownership, all that fun stuff. You'll see it in the title, and you'll understand what I'm talking about now. Okay. Sorry, I just want to breeze through that because we did learn that last chapter. Creating different types in tuple structs. Rust also supports structs that look similar to tuples, called tuple structs. Tuple structs have the added meaning the struct name provides, but does not have names associated with the fields. Rather, they have the types of the fields. Okay. So tuple structs are useful when you want to give them the whole tuple and name, and make the tuple a different type of other tuples. And when naming each field, as in the regular struct, would be verbose and redundant. To define a tuple struct, start with the struct word, the keyword struct, and then the struct name followed with the types of the tuple. For example, we're defining use two tuple structs named color and point. Okay, so we have a tuple struct called color and a tuple struct called point, and all of them are using 3 i32-bit or integers within that struct. We can see in the main function that we have another 2 set of variables called black and origin, and we're utilizing the tuples from color and point, the tuple structs that we're using in color and point here. So we're inputting the parameters here. Okay. If you understand what I'm saying, the color is black because it's 0, 0, 0. Point is 0, 0, 0. So that's the origin of it. I guess we're looking at those values. So note that the black and origin values are different types because they're instances of different tuple structs. Each struct you define is its own type, even though the fields within the struct might have the same types. For example, a function that takes a parameter of type color cannot take a point as an argument, even though both types are made up of three I32 values, so they need to be separated. Otherwise, tuple structs instances are similar to tuples in that you can destructure them into their individual pieces, and you can use a dot notation followed by an index to access the individual value. Unlike tuples, tuple structs require you to name the type of struct you struct when you destructure them. For example, we would write let point, and then we're going to do x, y, and z within the parameters as we're destructuring it equal origin. To destructure the values in the origin point into variables named x, y, and z. Easy enough. I feel like we've learned kind of the gist of it within the previous chapters. So going through structs, like you can kind of understand, we already talked about tuples. We can kind of understand what it is pretty quickly, okay? Define unit-like structs. So you can also define structs that don't have any fields. These are called unit-like structs because they have, similarly to our parentheses, the unit type that we mentioned in the tuple type section. Unit-like structs can be useful when we need to implement a trait on some type, but we don't have any data that you want to store in the type itself. We'll discuss traits in chapter 10. Here's an example of declaring and instantiating a unit struct named always equal. Okay, so we have our struct always equal. There's literally nothing in it. Then we have our main function. We're binding subject to always equal, which is our struct. To define always equal, we use struct keywords and then name what we want. Then a semicolon. No need for curly brackets or parentheses. Then we can get an instance of always equal in the subject variable in a similar way, using the name as we defined without any curly brackets or parentheses. Imagine that later when we implement behavior for this type, such as every instance of always equal is always equal to every instance of every other type, or any other type. Perhaps to have a known result for testing purposes. We wouldn't need any data to implement that behavior. You'll see in chapter 10 as we define traits and implement them on any type, including unit-like structs. Okay, ownership of struct data. In the user struct definition of listing 5-1, we use the own string type rather than the little string type or ampersand string slice. This is deliberate choice because we want each instance of the struct to own all of its data and for that data to be valid as long as the entire struct is valid. It's also possible for structs to store references to data owned by someone else, but to do so requires the use of lifetimes. We haven't even gotten to lifetimes yet. A Rust feature that is only discussed in chapter 10. Lifetimes ensure that the data referenced by the struct is valid for as long as the struct is. Let's say that you try to store a reference in a struct without specifying lifetimes, like the following in source/main. This won't work. So we have a struct called user, we have active, username, email, sign-in count, we have two strings, and then we also have a bool, and this is an integer. So for our main, we have let user1 bind to this struct, which is user. Active is true, username is this some username 123, email is someone at example.com, sign-in count is 1. So the compiler will complain that this needs a lifetime specifier. So we're doing a cargo run. You see over here where we have this little string, these strings right here, expected a lifetime parameter. And our lifetimes are categorized with this little quotation mark. It wants, oh my god, it wants a lifetime parameter in front of them. Oh my goodness. Am I losing my voice? But the thing is, I think because it is on the stack, these ands on the stack, these ampersands are a reference to a string on the stack. That's what I'm trying to get at. The big string is on the heap. Okay, remember that? So it's saying we haven't even gone into lifetimes that much, and I don't know too much about lifetimes. I just know that we utilize lifetimes as like it says over here, it's the time is the life of the struct, the amount, the scope of the struct, and then that's when the lifetime ends. So yeah, we're gonna have to get into that when we get into chapter 10 because I don't know too much, but I know the gist of it. Okay, an example program using structs. To understand when we might want to use structs, let's write a program that calculates the area of a rectangle. We'll start by using single variables and then refactor the program until we're using structs instead. So let's make a new binary project called rectangles that will take the width and the height of the rectangle specified in pixels and calculate the area of the rectangle. Whew. Okay, I encourage you to open up the projects folder, go in, try this as well. I am just going to read it to you. Yeah, most of these you can compile here, depending on if they have a print line. Lovely. See, this one has a print line. Now you can see how it runs. So, but I encourage you to go and type it out. The more hands-on you get, the better you get at learning Rust, syntax, all that. I also have a mini Rust series, a little promo here, mini Rust series that's coming out tomorrow, I think. Tomorrow, I already filmed all the videos, I just have to edit them and then upload them. So if you want to go check that out as well, go and try those projects out on your own. You can also download it, a local copy, or you can download it, my repo on your local machine. To go and do those projects on your own in your own code editor, okay? Okay, so here we go. Function main, let width 1 equal 30. Then we have let height 1 equal 50. We're print lining the area of the rectangle is blank square pixels. We have the area and the width that were over here. I don't know if you want to do that. Okay, so we have another function called area, and we're calling area over here with these two parameters that are U32, width and height. And then it's over here, it has width 1 and height 1, which are these. Okay, interesting. Okay, and then it's returning a U32. So it's utilizing this width and height, this width and height over here. Wait, what? Oh, sorry, I'm so sorry. It's binding this width and height. You see it's over here, the parameters that we have over here, returning an U32. Then we have this expression that's happening. So we're multiplying width and height together. Then in main, we have width 1 equal 30, height 1 equal 50. So for the area of the rectangle, blank square pixels, we're going to call area, we're going to call area, and we're going to have this expression with these parameters, these as the arguments. So it's going to be width, which is 30, times height, which is 50. It's going to be 100. And 1,500. I don't know why in my brain it didn't register correctly, but I think we made it through. Okay. Alright, so we ran the program. We got the area of the rectangle is 1500 square pixels, and the code succeeds in figuring out the area of the rectangle is being called by area function, which is a dimension. But we can do more to make this code clear and readable. See, sometimes when you're reading code that isn't as clear, it's a little bit difficult for your mind to wrap around it. And that's why you want your code to be as clear as possible, so when other people are reading your code, they understand what you're doing, okay? And maybe you would have not as many comments so that people can understand what you're doing. Okay, so that says function area. Oh, the issue with this code is evident in the signature of area, okay? So function area width U32, height U32, and returning U32. The area function is supposed to calculate the area of one rectangle, but the function we wrote has two parameters, and it's not clear anywhere in the program that the parameters are related. It would be more readable and more manageable to group width and height together. We've already discussed one way to do this in the tuple type. So, okay, so this is a little bit easier to read. We're gonna have function area, and then we have our parameters as dimensions, and the dimensions are together, okay? And then we're also going to have returning a U32. Now we have dimensions, and then this is dot notation, so we have 0 and dimensions, and then this is 1, okay? Over here in main, we have let rect1 equal 30 and 50. So these are related. Seems like they're more related now because they are grouped together. Now, when we have print line, we're calling area, which is our function, and using rect1, which is 50 and 30, and right here in our expression, we're multiplying both of them together. So it's going to be 1500. So let's run this. It's got the same output. It's just a little bit more clear that they're together. In one way, the program is better. Tuples let us add a bit of structure, and now we're passing just one argument. But in another way, the version is less clear. Tuples don't make their elements, so we have to index into the parts of the tuple, making our calculation less obvious. Mixing up with the width and the height wouldn't matter for the area calculation, but if we'd want to draw the rectangle on the screen, it would matter. We would have to keep in mind that the width is a tuple index 0 and the height is a tuple index 1. This would be even harder for someone else to figure out and keep in mind if they were to use our code, because we haven't conveyed the meaning of our data in our code. It's now easier to introduce errors. Refactoring with structs. We use structs to add meaning by labeling data. We can transform the tuple we're using into a struct with the name of the for the whole as well as names for the parts. Showing in listing 5-10, here we go. So we have a struct named rectangle, we have width and height. And then I'm just going to go all the way down here where we have a function area where rectangle is referencing our struct called rectangle. We are now going to return a U32 number, and we're adding rectangle, and we're dot notating width times rectangle times and dot notating height. Okay. So we don't know what width and height are yet until we get here. So we have function main. We're letting rect1 equal rectangle, which is our struct. Within that rectangle, we have width, which is 30, height, which is 50, and then here we're going to be print lining how many square pixels it is with the area that we're referencing here, or we're calling this function here, and referencing rect1, which is our variable here. We can run this, and we get the same thing. Okay? So many ways to do the same thing. There's just easier ways to do it. There's more clearer ways to do something. Yeah. Here we define a struct that's named rectangle. Inside the curly brackets, we define the fields of width and height, both of which are U32. Then in main, we have a particular instance of rectangle. This that has width of 30 and height of 50. An area function in which defined with one parameter, which we've named rectangle, whose type is immutable borrow of struct rectangle instance. As mentioned in chapter 4, we want to borrow the struct rather than take ownership of it. This way, main retains its ownership and can continue, using rect1, which is the reason why we use the ampersand in the function signature where we can call the function. Okay? The area function accesses the width and the height fields of the rectangle instance. Note that accessing fields of a borrowed struct instance does not move the field values, which is why you can often see borrows of structs. Our function signature for area now says exactly what we mean. Calculate the area of rectangle using the width and height fields. This conveys that width and height are related to each other, and it gives a descriptive name to the values rather than using the tuple index of 0 and 1. This is a win for clarity. And it's always nice to be very clear within your code. Adding functionality with derived traits. It's useful to be able to print an instance of rectangle where we're debugging our program and seeing the values for all of its fields. Using listing 5-11 tries to use a print macro as we've used in previous chapters, but this won't work, however. Now we're looking at our struct, which is rectangle. We have a width and a height, and both have a U32. Function main, we have let rect1 bind to a rectangle, which is a struct, and we're inputting 30 and 50. Over here, our print line is rect1 is rect1. Now, why won't this compile? When we compile this code, we get an error when we get an error with this core message. Rectangle doesn't implement standard format display. Okay. Now, print line macro can do many kinds of formatting. And by default, the curly brackets tell printline to use formatting known as display. Output intended for direct end user consumption. The primitive types we've seen so far just implement display by default because there's only one way you want to show a 1 or any other primitive type to a user. But with structs, the way to print line should format the output and is less clear. Oh my god, I cannot read today. When can I read? Oh my gosh. But with structs, the way print line macro should format the output is less clear because there are more display possibilities. Do you want commas or not? Do you want to print the curly brackets? Should all the fields be shown? To this ambiguity, Rust doesn't try to guess what we want, and the structs structs don't have a provided implementation of display to use with printline and the curly bracket placeholder. Let's take a quick drink. I think this is going to be the last one today. We can do methods tomorrow. I think I might just mash up methods and enums because I like them put together. So let's do methods and enums tomorrow. We'll finish this one out. Let me see how long this video is. I don't even know how long this video is. Oh, 34 minutes. It's only been 30 minutes. I just have a lot of things to do today, so I'm just going to mash them together. Okay. Where are we? Okay, so let's try it. The println macro call will now look like println, and then we have rect is rect1 in the curly brackets with a colon and a question mark. Okay, putting that specifier colon question mark inside the curly brackets tells println we want to use an output format called debug. The debug trait enables us to print our struct in a way that is useful for developers so that we can see the value while we are debugging our code. Okay, compile that code with this change, drop. We still get an error. They knew this. They knew this. This was premeditated. But the compiler gives us a helpful note. Required by this formatting parameter. Okay, so Rust does include functionality to print out debugging information, but we have to explicitly opt to make that functionality available for our struct. To do that, we add the outer attribute, derive debug, okay, just before the struct definition, as shown in listing 5-12, and we're going to be using this derive debug a lot. Oh, so we have derive debug, we have our struct within our main function, we also print it out with our colon, and then our question mark. And let's see if it's wrong. Yep, rect1 is rectangle, and then over here we have our curly brackets. Width 1, our width is 30, and our height is 50. Now we run the program and we won't get any errors, and we see the following output. Nice. It's not the prettiest output, but shows the values of all the fields for this instance, which will definitely help during debugging. Whew. Okay. When we have larger structs, it's useful to have output that's a bit easier to read. In those cases, we can use a colon, a hashtag, and then a hashtag or pound, and then a question mark instead of a colon question mark. In the println string, in this example, we use a colon hashtag question mark for the style of output of the following, okay? So this one is a little bit different. You see how everything was on the same line. On this one, a little bit more prettier. This is on different lines, okay? Another way to print out the value before the debug format is using the debug macro, which takes the ownership of the expression, as opposed to println, which takes the reference, prints the file and line number of where the debug macro occurs in your code along the resultant value of that expression and returns ownership of that value, okay? So calling debug macro prints the standard error console stream, which is standard error, as opposed to println macro, which prints the standard output console stream, which is standard output. We'll talk more about standard error and standard output. Okay. Here's an example where we're interested in the value that gets assigned to the width field, as well as the value of the whole struct in rect1. So we have a derive debug on our struct rectangle with width and a height of U32s. We have our main function. We have let scale equal 2, let rect1 equal the rectangle struct that we have over here. Then we have width with the debug macro 30 times the scale, which would be 60. Height is 50. Then we have debug again. Our debug macro is referencing rect1. So I'm pretty sure that would be 60 and 50. Yep. Okay, so we can put a debug macro around an expression in 30 times scale because debug returns ownership of the expression's values, and that in width field will get the same values as if we didn't have the debug there. Okay, we don't want debug to take ownership of rect1, so we use a reference to rect1 in the next call. So you can see at the end it's debug macro reference to rect1. Okay, this is how it compiles. Rect1 equals rectangle, and then width and height. Oh my goodness. Okay, we can see the first bit of outcome came from source/main.rs line 10, where we're debugging the expression 30 times scale, and its resultant value is 60. The debug formatting implemented for integers is to print only their value. The debug macro call on line 14 of source/main.rs outputs a value and rect1, which is the rectangle struct. This output uses the pretty debug formatting and rectangle type. The debug macro can be really helpful when you're trying to figure out what the code is doing. In addition to the debug trait, Rust has provided a number of traits for us to use with the debug attribute derive attribute that can add useful behaviors to our custom traits. Those traits and their behaviors are listed in the Appendix C. We'll cover how to implement these traits with custom behavior as well as how to create your own traits in Chapter 10. There are also many attributes other than derive. For more information, see attribute section in the Rust reference. Our area function is very specific. It only computes the areas of rectangles, that would be helpful to tie this behavior more closely to our rectangle struct because it won't work with any other type. Let's look at how we can continue to refactor this code by turning the area function into an area method within our rectangle type. And that's when we're going to be talking about methods. It's going to be tomorrow. I know this is a bit of a short one. I just have some editing I have to do, and I really want to get out the other videos that I completed today as soon as possible for you to do these practice projects with me. So it's going to be so much fun. It also is Smiling Friends themed. If you don't know what Smiling Friends is, it's a cartoon on Adult Swim, and these coworkers are tasked to go and help people and make them smile. So it is actually really funny and bizarre and stupid, and I really do love that show. So I wanted my Rust series to emulate that as well. Let me put this up. I am so glad that you guys are going through this series with me. I'm going to try and do it Tuesday through Friday as per usual. And I see you tomorrow.